that's the nicest page of the presentation on it. I like that. I like the colour. After that, it's got information that you may have seen before. The books, actually, we changed the technique. We did it all together. You can see the methods books are actually published. What happened was that they were sent across, the old books were sent across to India, and they were changed into LaTeX in India. But then after that, we actually wrote them directly into using LaTeX. So the setting out is done with people with mathematical knowledge. And we had a very good editor, Dr. Jane Pitt-Kethley, who's a research fellow out at La Trobe. And so she was working with us too. So there's a further check on accuracy. Our editor was a PhD who's meticulous. I can tell you she's meticulous. She's one of those people. So we actually we've added to the quality, and I can say that with some confidence. And the setting out, if you look at it, it actually just looks nice mathematics. And I don't want to wax lyrical too much about it, but I like LaTeX, and it gives great power to change into HTML too. When you write in LaTeX, and people should know about it to some degree, it switches straight into HTML. And that's how, when the books are on the web, they'll look in very good form, because, you know, the sort of thing where you get images distorting when you stretch. LaTeX doesn't do that because it's run on Google Fonts. It's run on Google Fonts once you're in HTML. So it actually is much more stable and attractive too. I only say those things because I was really interested in doing it, and I can say it took a lot of hours doing it that way, but it gave us complete control over it. It wasn't going off to an independent typesetter, and it wasn't changed. It just went straight to the printers from us, more or less, and it felt much more satisfying. I recommend it as a way to write books. As a person that spent too much time doing that, that's a good thing to do. Okay, let's just do this. General changes. And people are looking at this and thinking, oh no, not that again. Okay, here it is. The possible pathway from Foundations Mathematics Units 1 and 2 to Further Mathematics Units 3 and 4, developing a distinct specialist maths course, Units 1 and 2, using the same flexible structure as for General Maths Units 1 and 2. I do want to say something about that straight away, because really the new subject Specialist 1 and 2 has got no negative aspect to it. Everything you could do with General Maths you can do in Specialist 1 and 2. The only thing is that now you give them credit. If they've done the harder course, you can give them credit. Before, you know, you had your advanced general class, or you had students doing a harder work, and they got general maths just the same as everyone else. Well, now you can give them specialist maths. And it's sort of got a nicer ring to it, that they get credit for doing it. And it may be a selling point rather than some people feared initially that it might put people off. But really all you do is sell it as, really all it's changing is that we are now giving credit for you doing harder work. And that is the way to sell it, I think. Okay, the redevelopment of further maths with a 60% core and 40% module structure. Look, some people see this as not a massive change, and probably if you're in there, you'd actually hear Peter saying there's really quite big philosophical shifts, but basically the material is the same, but shifted into the core. And when you read through the syllabus, you'll find that, and when you look at the book, there may be a bit of change in the pedagogical emphasis, but really that material has been there. But it's a substantial change that now that 60% is common. And obviously with those modules always cause trouble with trying to get them of equal difficulty. The last one, the inclusion of statistics, content, and mathematical methods in specialist mathematics. Look, I can say I've spent probably 4 years living through this change, because it was in the Australian mathematics curriculum. The curriculum was developed by Cara, and I was a writer for that back a few years ago. It's probably 3 or 4 years now. Was done under really needed government direction. In fact, it was government direction. The statistics was going to be part of senior maths courses in Australia. That was a government direction. Through the ABS put pressure on, and then in actual fact it went through that we wanted to have more statistics in our courses. I think I can say we did a really bad job last time we had statistics in math methods. When we had confidence intervals here, I think it was back 95, something like that, 96. We just did a bad job. I can say every aspect of it. And when you saw the exam questions and what we were asking and what I knew about it, maybe I'm talking to myself, I did a bad job. So I know I did a bad job because I didn't really have a complete grasp of the direction. what we should see is, in actual fact, it's a culmination of all the students' work in statistics and probability right through the school. And it gives purpose to the probability that you do in year 12. Right? Certainly you can't do any of the sampling distribution unless you know binomial and normal. Right? It doesn't make sense. So all of a sudden there's a real reason for doing a normal and binomial, that you can't do this very useful activity of working out sampling distributions. And when you think about sampling distributions, all you really do all the time, and I'm going to write it up now even, is that if we've got a binomial distribution x, right, and we work out, we divide by, we take samples of size n out of a binomial population. Just think of red balls and blue balls, that will do, right? And we take samples of size 20, then x on n, that's just 1 on n times x, right, is the sampling distribution random variable. That's all it is, multiplying by 1 on n. What do we call that one? You see it in the study design, I'm going to say it. We call it big P hat. The sampling distribution random variable is just a binomial divided by the sample size. So you actually have your sample, you have your population, let's say, and then what you do is you take out samples of, let's say, a size 100. You get all these samples out here, and let's just say there's 1,000 in here and 500 red, say 500 red, 500 blue, just for ease. And what you do is you get a, let's just say you got a sample size of size 100, and we took x is equal to 45. What does p hat equal to? It's equal to 0.45. That's all it is. Never be scared about this topic. That's as simple as it is. All you do is you do random variable, binomial random variable, divide by the sample size, and you have big P hat. You're in business. Right? Once you get that, there's not that much more, I can tell you. And you ask the same questions for big P hat that you've asked for x. You can ask, what's the probability of big P hat being greater than 0.3? What's the probability of big P hat being greater than 0.3, given that it's greater than 0.2? They're all legitimate questions. And all it is this random variable, 1 on nx. And what do we know about this thing? We know this, don't we? This will just make it a little bit more obvious, because that's 1 on x. We know the rules for this. What's the expected value? It's p. That's what you'd want it to be. Right? And so the theory we know fits in here. It's a nice unbiased estimate. We get the proportion of the population. This p is the population proportion, right? This is the population proportion here. The proportion of reds is just p. What's the variance? I'm going to do it because it makes it look easy, and then you know what a lot of these symbols mean. The variance of x is p hat, I should say. P hat is equal to the variance of x on n, and how do we make sure that that works? All we do is put it's 1 on n squared into np1 minus p, isn't it? Right? And so what do we get from that? This is the number in the you see in the study design. It just becomes p times 1 minus p on n. So what's the standard deviation, the square root of it? You understand the study design when you see that. That's all it is. Right? You can teach it as quickly as that. This diagram here is absolutely essential. From here, what you can do, of course, is do this fella here. Right? You can do 0.5, 0.4, 0.6, and you can do the number of occurrences of these things. And you see, just like you do for binomial, there's a nice distribution being formed. And one of the nice things is the calculator does this. The calculator does the simulations, right? You say, I want to work with a binomial population. I want to take out sample sizes, and a binomial population, let's say in this case, right, with p is equal to 0.5. And we take samples of size 100, okay, and you can set that up in the calculator. You can fill down, you can do 1,000 of them easily, and you get your distribution coming through. So you get pictures of this distribution process. You get this graph coming out on the calculator. It's what I often say, as people know me, that I'm not really a calculator crazy person. I I can use calculators, and I've always lived with them. But with this, forget it without it. Right? This is a calculator. They really understand a lot more when you use your calculator properly. It works with both Casio and with TI. And the instructions are given in the books, obviously. We're actually doing the TI and Casio appendices will be online material. You can download it. The books already, you can see the size of them. They're too big. So you can download, when you buy the book, you get access to the calculator appendices. And there'll be fuller explanations in the old appendix. So you'll be able to go through that through using the appendix too. Okay, that's my cell of the statistics. I think there's something over the page. This is important too. Right? I want to draw everyone's attention to this because it was put down, these dot points I think came from the VCE originally. I have a strange feeling they did. Because you transfer them from presentation to presentation, you don't know where things come from, but you think they come from there too, don't you? Yeah. This is changing, right? The SACs are changing, and you have to be aware of that that difference, because it's not so much in the application task. The application task is going to stay more or less the same, but in the no longer can you do those series of tests for the other SACs. It was considered by the committees that what people were doing is just replicating what you were doing in exam 2. And okay, we understood the reason for that, but the decision was made that we wanted to actually vary the way people were being assessed. So now the switch is into a modelling or problem-solving task. The difference is you can still set tests, and you don't want it to be blown out into something huge, but it actually has to be along a single theme. So in specialist maths, for instance, you do something like different ways that populations increase and decrease using different functions. It's an easy problem-solving task, isn't it? How things drop out of planes, right, with different resistances and that sort of thing. You get a whole family of problems which are related, and the student investigates more as they go through, and they can do it using a variety of techniques too. Look, there's some things in here I've called them major changes. There are other things you'll find. I know that if you went to Alison's talk, for instance, on math methods, and I've got a copy of it, there's little bits underlined in red occasionally where it changes. They don't really change what you do very much, most of them though. They really pick the difference. And you can do that yourself if you like, go through the 2 study designs and change. But the major things are here. There's no Markov sequences. We've got bisection and Newtons, which I don't think is causing anyone any trouble by the sound of it. People are just saying, okay, I can do that now. As an examiner, I'd say, just roughly, it's unlikely bisection and Newtons would be tested in year 12. It's unlikely, isn't it? Just like the old, you've even forgotten iteration techniques was in the old syllabus, haven't you? Right, because no one taught it after a while. Now, what I'm saying with this is, it's good to do because it makes people understand more about what's going on. In fact, more so than the iteration technique, and that's why it was changed. And it helps them to understand functions. It helps them to understand differential calculus. So it's good to do pedagogically, but it's very unlikely that questions would flow through into year 12. Okay, and we've got no functions involving absolute values. I know people started teaching absolute value function in year 11. That's migrated completely. Why did that happen? Well, simply we noticed that people were spending a huge amount of time on it because the examiners in their, whatever you like to call it, kept on asking questions on nasty functions with absolute value around it. So everyone spent a lot of time, okay, draw this graph, now take the absolute value of it. You know how much time that spent. Everything you taught actually kept on coming back to that, and then you had to solve equations with absolute value. That's gone from 3-4, okay? So I will add something to that now even. If I was teaching the integral of 1 on x dx, I would still teach them that the integral was log e absolute value of x. I'd still teach that, right? Even though it's not in the syllabus. They can't be marked wrong. Their calculator gives them that result, but also it safeguards them against negatives, right? It's a safer answer, isn't it? At the same time, they should know how to split it up if necessary. So there's a little bit of work, but it's very focused. It's focused on just integral of 1 on x dx, right? The integral of 1 on x dx and its transformation. That's the only context I'd teach absolute value in. I think it actually helps, and it is in specialist, but doing it in methods won't hurt. I would certainly do it there. And Markov's gone altogether, which we all bemoan, but things had to go. Everyone said the course was too big, so that's been cut back. Rational root theorem, I won't go through it now. More or less, it gives you another way of finding roots which are not integer solutions. That's an easy result in a sense. I'll read it out. Consider the cubic polynomial, 2q minus x squared minus x minus 3. If you're up there, it's probably easy to read. It's on that one too. Okay? If you're here, it's better to read this one. It's a bit small, isn't it, probably? You okay? Okay. Oh, okay, that's right, good, yeah. I took a snap, basically. I didn't type it up again for obvious reasons. So it's snapped. Hence the equation has no solution that is an integer because the factor theorem tells us that. It doesn't have a rational solution. That is a fraction for a solution. The rational root theorem helps us with this. It says that if alpha and beta have highest common factor 1, e.g. 2 and 3, 7 and 5, 6 and 11, right? Anything like that. They're relatively prime. And bx plus alpha is a factor of that, then beta divides 2, right, the leading coefficient, and alpha divides -3. So the implication says that if it does, then you get that happening. That's a way to test whether something is worth going on with. Understand? It's a test to see whether you keep going. Once you've found out that they do divide into it, well, you've chosen them so that they do divide into it, then you actually have to test using the factor theorem. Will this flow into 3, 4? Yeah, I can't see why it wouldn't. In exam 1, it could flow through, couldn't it? It'd be a totally reasonable expectation that now the students understand the rational root theorem. Not hard. The proof is a little bit number theoretic. And I know we go to some effort in here to do the proof, but I think we're thrown into an appendix, right, to keep it safe, basically, so the students don't get scared, but you can do the proof if you want to. That reminds me, actually, on the same topic, I know a lot of people use synthetic division now, and that also is in the appendix, how to do division of polynomials using synthetic division. So that's there as well. If you want to teach that, it's there. I think the other thing with polynomials that's in here too is that we've done the step-by-step explanation that, of what happens when you're doing long division too. So they're all related things. Okay, Deb has actually pointed out, when she looked at the book, she said, you've still got all those matrices in there. That's a book. You have to choose the emphasis. The matrices you have now in the course are really diagonal matrices, right? Dilations from an axis, reflection line y equals x. They're all diagonals. You don't really need matrices. Some people actually argued against matrices being retained. But as soon as they're there, you actually have to have some level of understanding of them. You'd spend less time on it, that's all. And you wouldn't do endless examples with anything beyond 2 by 2 matrices, really. That's where you draw the line. The other question that comes up, what about when you actually have simultaneous equations in 2 variables, right? And you're asked the values of m, a parameter such that there are no solutions, unique solution, infinitely many. The answer is that's still in the syllabus, of course. But now you haven't got matrices and it's not mentioned in relation to that. But you can still do that problem, can't you? Because you can do it with gradients. Now, is it easier to do with a determinant? Some people think it is, right? So you're free to teach that. But you don't need it, right? You don't have to do it. So the examiners can ask such a question. I think you all know what I'm talking about, don't you, in methods, where you have the m's and you ask the values of m such that it can still be asked, right? Because it's not a matrix question, it's a simultaneous equations question. So certainly tone back what you do in, bring it back a bit in matrices. but they'll need some fundamental understanding of what it's about. They'll certainly have to know how to multiply them, and certainly they'll have to be very good at multiplying and manipulating diagonal matrices. Of course, if you have a diagonal matrix which goes 2, 3, the inverse is pretty easy, isn't it? Right? It's a half, a third. Life's easy, right? With diagonal matrices. You don't need any theory, really. So you can do a lot with just what you've got. Okay. No related rates of change. We had about a decade of that, didn't we? It wasn't there before. We brought it just went out because something had to go. Obviously, it's expendable because it didn't used to be there. It's a pity in some ways, isn't it? Because it actually takes away that connection with the chain rule and shows that there's a nice application. I understand all that, but at the same time, everyone says there's too much, so things have to go. Oh, functional equations are still there.
What if you have it in terms of more than 2 variables? And if
Look, the complexity is a question. I mean, but you'd certainly have to know, say, for e to the x, right? You'd have to know f of x plus y is equal to f of x times f of y. I mean, all those things are expected still. Yeah, okay. Y is in terms of something else.
So you get a third variable thrown in.
You're asking a different question here, aren't you, I think. What you're asking is if you need a parameter, okay, in the solution of the simultaneous equations, right? So if you're in x, y, and z and you need a third parameter, the answer is that has not been ruled out completely if you look. So such a question can still be there, but it has to be done without matrices. Okay, so it has to be fairly simple. So it could be x plus y is equal to 3, x plus y plus z is equal to 2, right? Let y equal lambda, right? They have to know what that is. It hasn't disappeared. It's there gently, though. So the expectation from now on, any such, correct me if I'm wrong, but I don't think we've had questions on it.
No.
It's a bit of a no-no, really, because it still can be there, though. I mean, it'd be quite entitled to. Especially in exam 2, there could be an analysis question where it's appropriate to bring that idea in near the end of a question. And the student would be expected to be able to do it. So I can't rule it out. That would be very dangerous of me to do so, yeah.
I just wondered if you could speak up, please. I'm struggling to hear.
Oh, really? Okay. Always say that. Is anyone else having trouble hearing me? No, I start talking to someone down here like this, you see. Yeah, I'm sorry. Always, yeah, please do. I get used to, I had one session where I had someone in the back row yelling at me all the time, so feel free. Andrew will yell at me from now on. Well, maybe not. He sits opposite me here, so. Okay, so, and the important thing at the bottom here, the distribution of sample proportions. I can assure you that's not going to be a huge amount of work, right? I hope from what I've said you can see the connection, right? By the way, when you get that distribution, why do you go to normal? You go to normal afterwards because there's a normal approximation to the binomial, which we used to do, which has now gained importance again, right? That's what you're doing. That's why you start bringing in z, etc., and you see it there. It's simply that you've done the normal approximation to the binomial, which is a very easy step, as long as you wave your hands like this and say, yeah, they're the same shape and it's good. That's all it is. And all you do is say it's normal with mean, the mean of the random variable that we had, and the standard deviation as before. So we know everything about that normal distribution once we've got it in good state. Okay. How many people are interested in specialist maths here? I hope, oh yeah, good. Okay. I was somewhere this morning and I was speaking to, there was 20 people in the room and 2 of them were specialist maths teachers. And I started going very fast. Specialist 1 and 2, there's things to watch here. There's areas of study, right, which are listed there. Areas of study which are listed there. They overlap with the areas of study of general maths in the sense that they're nearly the same as the areas of study of general maths. And before I go on to slides and keep progressing, it's very important to notice that in actual fact you can use general maths topics in specialist maths. Everything that's listed in general maths you can do in specialist maths. So if you wanted to emphasize a particular aspect, You can pick something out of general maths and put it in the specialist maths. There's a lot of flexibility here. The other thing is, this is a year 11 course. And I can say, as we go through, you'll see that some of these dot points include a great amount of material. I would say that you could spend a term on them if you really wanted to do, if you really wanted to go wild on a particular topic. The answer is you don't. You pick and choose inside a topic and you put the amount of emphasis on things you want to. You're obliged to actually address each dot point, but the emphasis you put on it can vary greatly. It can be a conversation for 2 minutes in a class, or it could be a week. There's no prescription of time inside the topic. That's very important when you're looking at it, because quite frankly, when I look at some of the topics, I think I could teach that for the whole year. Right? If you look at the specialist maths one, you think, oh, it's about a year's course there. You don't have to do that. You can pick what you want to do in particular. Okay. Okay, I like the dot point. What you do is you choose ones which are going to be useful. There. That makes sense, doesn't it? Okay, this is the number systems and recursion. What it's got in it, it's got huge amounts of material in it. It's certainly got everything about sequences, right? Recursive relationships, mathematical induction, complex numbers, properties of primes. It's about a 2-year course. No, it's not. What you can do is select what you need to do out of it, though, right? It's a very big one, this first one. You can say, look, I really need that for next year, but you can choose to actually just acknowledge some of the dot points, right, and emphasize the parts where you feel as if it's very important. So most people will do the complex numbers, for instance. I would always do sequence and series. Now, when I say that, what I'd do at the same time that I was doing number systems and recursion, I'd actually do the general maths. I think it's called recursive relations or something, but it's really sequence and series. Right? I do that at the same time. I get 2 topics for the price of 1. I say do things like this because you can actually fill this course up very quickly. Just look for the overlaps, basically. That's a good thing to do. If you want to teach variation, for instance, which I still think, I know some people don't share my opinion on this, I still think that variation is quite a good topic to teach in year 11. And it's not in specialist maths, but it is in general maths. So you can take that out of there and teach that as one of your topics inside that. Geometry in the plane and proof. I must admit, where I was this morning, they actually started to tell me about what's this proof stuff. The answer is we've had very little proof in our courses for a long while. It went out of fashion completely in about the late 70s, early 80s. I lived through it. Right? All of a sudden people said, you can't do that, it scares them. Okay, we changed that, so people said, what's the difference between show that and prove that? The answer is nothing. Right? The word show that was chosen, right, because it was considered less scary. And you have to go back to the 1970s, yeah.
So back in the dark ages when I was at school, we actually had to give a reason for every single line that we did.
Yeah.
Alternate angles are equal or whatever it is. Do they still have to do that?
My answer would be no in this context. In fact, I wouldn't do that deliberately. The same in geometry. I wouldn't actually start insisting on, for most students, I wouldn't insist on perfect setting out. What I want them to understand is the sequence of ideas. Right? You want them to understand the sequence of ideas and be able to explain that to you in some way. It can be just a diagram. I mean, the classic diagram always is this one, isn't it? And I keep finding people that haven't seen this, which is, I have got a duster here. It's just, yeah, don't laugh because a lot of people have seen it, but just that construction, right? I see that as a proof there's 180 degrees in a straight line. That's a proof. If the student actually does that, they understand it. They don't have to keep on cutting out bits of paper. If they understand that, they've got it. And they really got it. They understand why it works. Those ideas are equivalent. Right? I mean, the old proof, this fellow here, right? As soon as you do this, Aren't you happy if a student knows that? I am. And my feeling about the geometry in particular is that we do want to get the sequence of ideas through, but if the student can present even the diagram, it's showing they understand what the process is. That's a general student. There will be some students we would love to write out things beautifully. You have to choose that though. You know it can kill people if you start insisting on.
Yeah, I started doing it, it's killing my students.
Yeah. You have to choose how far you're going to go. But I like it when people can people read that scribble? It just goes x, 2x, y, 2y. Yeah. It's the proof the angle at the centre is twice the angle at the circumference. And it's a special case because I've only done one diagram. So that's the sort of thing you should be a little bit careful of, because if it's a good student, you'd also want them to worry about the other angles involved down here. You'd want them to know about that one too, right? You'd want them to worry about that and to make sure their proof is going to work there too. But it's going to be a degree, isn't it? Because if you're going to do that properly, you really have to look at cases. You have to look at cases and go through. The initial idea, though, is how all the cases work. All the cases work like that anyway. So you can go to town on cases and make sure that you've got the diagram, independent proofs, forget it. But look, the other thing, and this is really dangerous, you prove things like there's infinite number of primes. I did that with Year 7 kids yesterday. They understood that. It's a proof. All you do is say, pick your biggest prime, right? And they said 107. And then you take the product of all the primes which are less than that and add 1. Then that new number, right, must be prime, because all those prime numbers give remainder 1 when you divide in. So that was their biggest prime. Now you say, okay, now there really is, now assume there's a really big prime. There is a biggest prime. You do the product of all the primes less than that, add 1. I've got a new prime. Whoops. My initial assumption is rubbish. It's proof by contradiction. Kids can understand that. If you get too tied up in notation and start writing P1, P2, forget it. Get them to pick their biggest prime, because when you understand it for 107, right, you understand it for the big P, basically. So I would like to see that sort of spirit in proof. For the very able students, then they can start writing out beautiful arguments, and I'd encourage that. But it's not going to work for everyone. It just won't. We know that. I've been around long enough to know that that's a way of killing off interest. But the idea itself, most kids will love that, I reckon. Okay. So you've got geometry in the plane and proof and vectors. And everyone will teach vectors. All right, we know everyone will teach vectors. And this one here, the last one, it contains things like polars, parametric equations, reciprocal trig functions. So everyone will teach this one anyway. It's compulsory, but in actual fact, you teach it anyway. How much emphasis you want to put on polars after you've done complex back in the other topic, you can join them together a little bit if you want to anyway. Right? You can say, I've done that down there because I did that on complex numbers in that context. You can join it together. I think I probably can go about another 2 minutes. No one over there. Peter will talk for longer than I will, actually. This is the stuff people were asking this question at the beginning. You know, what does it mean? Specialist 1-2 is not a prerequisite for Specialist 3-4. You do not have to have done Specialist 1-2 to do Specialist 3-4, just as it is now. Is that a sensible thing to do? Not really that sensible, is it? Right? You'd want students to prepare beforehand, but there is no prerequisite statement. Therefore, we have to be very careful with what we say that students know when they come through. So there's these statements which are a bit wishy-washy about key knowledge and skills, which is a broader idea than the topic dot points. So it's nice when they've had that experience, basically, but it's not essential. And examiners will have to be incredibly careful about what they put in. Can proofs of by induction be in Year 12? I would be very scared as an examiner to do it without leading it carefully. It's in Year 11, it's in one of the prescribed topics. But if you do Demoivre's theorem, for instance, which is the classic in complex numbers by induction, it's really a 2-step, 3-step induction proof, isn't it? And do you have to do that formally? I don't think so. As long as you understand that you can go from n to n plus 1 in the process and they can see it keeps on building up, I don't think there's any problem with that. So again, the prerequisite structure is not strong. And that's what that's meant to say. It's best if the students have done it for their own mathematical development, but not essential. I can say that word now because we've changed the name of the books. Okay, there's some dodgy changes in here. The dodgy change is the first one, where hyperbolas and ellipses have been removed as a separate minor topic, but they're still there, right? That's the catch. Right, because they're in vector equations. Right? What you won't expect, though, is those, you know, the multiple choice questions you got at the beginning of the paper? Right, sketch this graph, etc. Which of the following is the graph of this equation? That's not really in the spirit of this change. It really should, the question should be asked is in the context of vector equations. Okay, so yes, they do have to recognise it's an ellipse or a hyperbola there, but they don't actually have to, they shouldn't have to do all of the same things. Do they have to know about asymptotes, or how do you do a hyperbola without asymptotes? I don't know. So the answer is yes, they do. They have to do asymptotes. So there's a bit of knowledge there which flows up. It just hasn't got the same intensity. That's how you describe it. Regions of the complex plane has been cut back, and it's always dangerous if I do this, but I know that there's lines, rays, and circles, right? Double check if, just so if I missed anything. But all the other things have been cut out. So strictly disks have been cut out, and infinite sectors are being cut out. Now, as soon as I say that, I would teach disks and infinite sectors. I would teach it just because it's such a, it's sort of a fundamental idea. That in actual fact, you've got the two rays going out, defined by the argument, or you've got the disk defined by the modulus being less than or equal to. It's fundamental understanding, isn't it? Can the examiners ask such questions? No. Right, they can't ask such questions. Okay, the absolute value function has been included, and obviously it's absolutely essential here because of the fact that you've got DEs, and we all know that. You remember those games you had to play when you didn't have the absolute value function? You had to manipulate for ages to make sure it could work, basically, with the problems. And of course you can always do it, but the absolute value function makes it a lot easier. The examiners now can apply this to anything. You have to know that too. I can't say the examiners won't apply the absolute value function to other things, right, to the other graphs of the course. Especially, I mean, just think of the nice questions, because rational functions now, if you just, I've just jumped down, rational functions have lost all their restrictions. You can just about do anything with a rational function now. So you can have graphs crossing asymptotes, all those things that we had 10 years ago, 15 years ago are back, basically. And they have to know equations of oblique asymptotes. This is quite a big change in a way, less restrictions on rational functions, because we're inclined to do very simple things. Partial fractions is in the same family. Partial fractions is now opened up. Strictly it says you can do anything with a partial fraction. Common sense tells you that it's going to be contained. So now you could do things like with the denominator x minus 2 squared times x squared plus x plus 1. Right? That's an allowable extreme question, isn't it? Right? It's not possible at the moment to ask such a question. So the answer is those two dot points after separation of variables does expand things out. It's one of those things where it's very easy to just change the wording slightly in a syllabus and then include a whole lot more work. And it's people who used to teach pure maths or maths B will go back to, it's back to those days basically, pure maths, maths B. It's back to that level. The same with partial fractions, it's back to pure maths, maths B level. Separation of variables. Separation of variables is really a, I think it's a plus. It makes life easier for you. The only thing is that it makes some new questions possible. I mean, the classic case is some of those outflow questions where you've got a Q on the top and a T on the bottom. right? Not a sum. That messes it up usually, unless you've got a common factor. Common factor with a sum's all right. But basically, if you've got a Q on the top and a T on the bottom, then you can split. Up to now, they've said you cannot do this question. And of course, you could do it, but you can now. You know what I'm talking about here? Things like this, as simple as this dq dt is equal to 2q on 3 minus 2t, right? You can do that now, just by splitting up. And it's not very hard. And the separation of variables, just in case, it's just this. It's just this step here. Excuse my probably dt on 1 over 3 minus 2t. Right, we can actually, have I done that? Yes, I have, haven't I? Yes, that's all right. I've done it properly. You can do that now. It makes life easier quite often, right? It actually makes life easier. I can tell you one place, you know, this expression here, this is another thing that separation of variables does, is, you know, the old one about this, d of half v squared dx. I have people come from overseas and say, what is that? I've never, what is that? No one uses that, right? No one uses it. But in Victoria, we've been brought up with it. I did it when I was at school, I think. I'm sure I did. Not sure. But in actual fact, because of this, right, and you've got separation of variables, there's no trouble now. Right, we can actually separate off the variables and we can anti-differentiate. So you don't actually need this anymore. You only need v dv dx. It's gone. I had, in the specialist maths book, I had a fight. One of my authors did a lot of teaching. He's Mauritian, and he was educated in London with Josie Astruc. And he went to London, did his master's there, and he said he came to Australia, did not know what we were talking about with this. It's very strange. It's only Victoria. The d of half v squared dx is very Victorian. There's no need for it because you can deal with everything with v dv dx. In the book, he argued that way. The other author said, we can't take that out. So it's still there. It's still there. Do they do that in Queensland? Do they do v dv dx? No, okay. Right. What else have we got? Yeah, sorry, I shouldn't do that too. I remember things, though. That's the trouble. I remember you were educated there. Okay. Limiting frictions out, you know those questions? You know, what's the least force to stop it going down the plane? What's the least force to get it going up the plane? That's out. Moving friction is still there. Right? Sliding friction. Sliding friction is still there. No question about it. That means coefficient of friction is still there. Right? Coefficient of friction is still there. There's no question about those things. The only thing is that situation, least force to pull up, least force to stop it going down. Right? Then arc length. Arc length is sort of a weird and wonderful thing. The only thing it does, there's a very limited number of examples you can do by hand. So it's nice for CAS, and I know that's why it got in, basically. Someone thought, like, we can ask nice CAS questions. And look, I know we've collected just about every possible function you can actually work out the arc length by basic techniques. So you can. I mean, there are some you can. But you know it's always this thing here. That's this thing here. I'm going to get killed in a minute. Oops. It's that, right? So it turns out to be nasty things, doesn't it? It's just Pythagoras, basically. Okay. And it's very nice to get the idea because you've done areas and volumes. Why not do lengths? The actual idea is nice. Including in the syllabus, I don't mind really. Okay. This last one, I'd love to have more time to talk about it, but I'm not going to be able to. It flows on beautifully from the methods topic. It flows on beautifully from the methods topic. But means is a little bit more complicated than proportions. They really do actually have to understand sums of random variables. I think that's really a key idea in the whole thing for the specialist people, that they understand random variables back to front. For instance, if you throw a dice twice, right, and you're going to add up the scores and ask for the probabilities of the sums, what you're doing is looking at the sum of identical random variables. Okay, that's really what's happening. It's the sum. You can work out the average of those two by dividing by 2. What you have to consider first, everyone knows this question from year 8, don't they? The Cartesian product, all you do is do all the ordered pairs, right, then add them up. Right, so what you do is you form the new sample space of x1 plus x2 by looking at the ordered pairs and summing them and working out the probability from that. They need to go back to that idea. They actually have to have a good enough grip of random variables to be able to play with it a little bit. Once you've got that, it's fairly smooth sailing. You can no longer use the normal approximation to the binomial. You actually have to use the central limit theorem. And the central limit theorem says that when I've got a distribution and then I look at the distribution of sample means, everything's beautiful if it's big enough. It turns out to be normal. It's one of the most remarkable results achieved in the 20th century, really. Everything turns out to be normal. So we can revert to the normal distribution. Doesn't matter how bad it is. Exponential distribution, right, really badly skewed off. If you start taking samples out of that population, what will happen in the end? The distribution of the sample means will be beautifully bell-shaped. You can see that in the AMSI modules. The AMSI modules have nice pictures, right? If nothing else, go to the AMSI modules and look at the pictures. Cambridge people are going to kill me in a second. I'm going to stop. Is that good? Yeah. Yep, okay. Yeah, I think I have. I don't think it gets interesting after this. I think I just talk about, oh, do you want to see those? You've got them, haven't you? Yeah, you've got, sorry, yes.
Just on that one there, I assumed that unit 4 was a single task, but it's actually 2 separate tasks.
Yeah. Yeah, the organisation's a bit different. Okay, so they're each worth 25% each. And I don't know if you noticed in the draft copy of the syllabus, originally it just had, oh no, I'm still in methods here. When I turn over to specialists, you had to do probability and statistics and specialists too, which would have been a real headache. Here's an issue for you. Sequencing not only your anti-differentiation integration with methods and specialists, you now have to sequence carefully your probability. And you have to think about it. You don't want to leave things to the end in both subjects. Somehow or other you need to be able to push up some of the ideas further into the year. So you might do discrete and binomial earlier in the year. You don't need integration. You might push that earlier in the year of methods. So they thought about it. Then the specialist teacher could set a little bit of holiday work on those ideas to start with. I know in the specialist work, even in the chapter at the beginning, what we've done is a quick look at some of the ideas out of sampling of means. Even in chapter 1. There's a little bit there that says, look, if the students want to think about it empirically during the holidays, they can. You can do quite a lot with your calculator. Okay, so there's math methods. I thought I was going to finish, but people started to look at it. Okay. The structure's changed, hasn't it? And just remember the requirements for these last two are different to now. You can't just ask exam 2 questions. Right, the application task strictly is exactly the same as it's always been, and you follow the same procedures. The other two are not the same, and you need to look carefully at what that can be. I've actually got a nice set of slides on that, but I won't. I think it's going to go up in the MAV. I'm pretty sure.
Those tasks should take a couple of classes each, running on the same thing. Is that right?
Yeah, 2 to 3 hours. Yeah. Yeah.
So the application task is in unit 2 for both specialists.
Yeah. Okay, the answer is the best thing for the answer is no. The intention is, are they going to be? Yes. But initially, one of the things to do is to look back at the old modelling problem-solving tasks from the old CATS situation, because there's lots of those, and this is probably just a bit of a tone down from that, because they weren't 2 to 3 hours. I'd be kidding you if we thought they were 2 to 3 hours. But yeah, you can do a subsection of the problem-solving that was there. So you can look and see what was done there and think, okay, I can just twist that round a bit, play with that idea. So if you've got those still, you're in business. The VCA occasionally talk about publishing them. Actually, Cambridge and the authors have got the rights on them, which is very strange. Cambridge and the authors have said to the VCA, yeah, go for it, as long as they're acknowledged. So hopefully, at some stage, the VCA will pop them up so everyone can have them. No one's holding on to them, but they exist. They still all have, I mean, I've got them at home. Sorry?
The MAB haven't got them somewhere.
Oh, I doubt it, actually. I doubt it. They might have some. I don't want to go on about that too much, but there's a CD with everything on it, basically, that was kept at that stage. So every single drop that ever came out was put on a CD, which still exists. Right? And the VCA have got that disc. So it's just a matter of them making that material available. Okay, I'm going to finish now. Thanks. Oh, no, okay.
Look at the sample retard exam questions
Yeah.
on the new statistics module.
Yeah. One thing that has been agreed to already is that there will be sample exams prepared in all subjects. They will not appear until after the examination period, because the VCA have got this thought that, you know, there's people out there who look at that and study for the exam. I don't think that, yeah, that's what the story is, so they don't come out until after the exam.
And just one more, when going back to years ago when mechanics was an option in specialists and statistics was 99% of people did mechanics.
Yeah.
Was that statistics module the same as this one?
There's a lot of overlap.
Sorry,
A lot of overlap.
because
So-
those exam papers aren't available
No,
online.
no.
And I didn't get
It was only for a few. It was only for a couple of years actually. That one
it's
wasn't
only
it?
a few years, like
2 or 3 years.
90 something.
Yeah, it was in the sort of around that 95, 96. It was only there for a couple of years because no one did it, so they just dropped it off. Reasoning and data. If you look up the old books on that, you'll find some relevant sections too. But they have to be regenerated. I think what will come out will be better than what was in the old stuff. Basically, that's my opinion. Because people have thought about it hopefully more this time, and certainly there's going to be sample examination questions. That's been agreed to, there's been meetings, they're up to that, so it would have to be some sort of funny hitch that stopped it. Yeah?
I wonder if there's been any comparison of the statistics to what the statistics module in the higher IBs, and that could be a source of
Yeah, higher IBs are
sample
sort of,
questions.
it's a little bit different though. When you read ours, it's very, very confined, so you have to be careful. It's not, I mean, deliberately been done, right? The only thing we do is look at p-values for hypothesis testing. That's all we look at. The IB does other things as well. So we're only looking at p-values. Yeah. It is, but the way, yeah, that's in both. But the hypothesis testing, IB goes further. Yeah. But the other thing, it's a resource, yeah, of course. So I'm saying that, but be careful. You just can't sort of carry it across. Yeah, that's certainly true. And I've been told there's some good examples in some of the IB texts. So. I think it'll be easier now. I think it will be. I'm going to keep on repeating. I think it will be easier. We can keep on doing that for a while. But you might look. I don't think it's that bad actually. Why are we doing it? Because people value it. That's part of it. It's an important part of mathematics. So it's being valued, that's all. No, it's quite a good chunk. It's a good chunk. There's a nice bit of work that goes through from methods to actually specialists. There's enough there for kids to get their teeth into. I've spent quite a lot of time on years. We could argue about that forever, couldn't we? But we won't. Okay, I think I am finishing now.